Can you see it?
Yeah,
Okay.
it's coming. So within couple of minutes we can start.
Okay.
So good morning participants. Uh, Now we have session on modeling of the contact line dynamics and its utility in heat transfer application. So till now we had sessions on computational mechanics for the solid modeling. But as we go for the smart materials application as well as the biomedical implants application, we need to also understand the thermal behavior. So from this session, we will able to understand how to computationally understand the behavior of any system in thermal or heat transfer sense. So for that, we have Dr. Pramod Kumar for this session. So on the behalf of participant, I must welcome our this session speaker. So with due permission of Dr. Pramod, I would like to briefly introduce our speaker. So Dr. Pramod Kumar is an assistant professor in the School of Engineering at IIT Mandi. Before joining to IIT Mandi, he also worked as a faculty in the Department of Mechanical Engineering at the NIT Hamirpur. He has completed PhD from the Department of Mechanical and Industrial Engineering, IIT Roorkee. His research expertise is in multi-phase flows, entertainment dynamics, CFD, solar thermal energy system. His research work is published in international repute journals such as Physics of Fluids, Chemical Engineering Sciences, and International Journal of Hydrogen Energy, etc. At present, he has published more than 20 research articles in international repute journal and conferences. He's also handling a sponsored research project in the broad domain of multi-phase flow. So with this very short introduction, I invite Dr. Pramod to carry on this session.
Thank you, Dr. Himanshu, for the nice introduction, and also I am thankful to you for giving me this opportunity to speak on the topic modeling of contact line dynamics and its utility in heat transfer applications. I hope my screen is visible to all and I am audible clearly. So while I'll be going through my presentation, I expect the interaction from all the participants. At any point of time, when you are having any questions or concerns, please feel free to stop me and ask your concerns. Okay. So let me start my lecture now. So here I have few keywords in my title. So first is contact line dynamics. Okay. And second is its utility in heat transfer applications. So let us first try to understand that what is contact line and what is contact angle and why it is important for heat transfer applications. After establishing its importance, then we will be briefly discussing about that how we can model this contact line dynamics. So to give you an idea what is contact line dynamics, I have given some of the schematic representations over here. So here you can see that we have some this black colored, this is nothing but a solid surface. So this black colored surface is a solid. Then this blue colored surface, we have some liquid. Okay, and this liquid we are calling as nothing but a drop. And outside this liquid, we have some surrounding medium. So in the normal atmospheric conditions, our surrounding medium is nothing but air over here. Okay. Now what happens? Uh, the point, so this is a two-dimensional representation of our solid, liquid, and surrounding air system. So in this two-dimensional representation, we will be finding that we are having over here some point where we have interaction of all the three phases. So at this point, you can see we have solid also present from this side. This side we have surrounding air medium also present, and from this side we have liquid present. So the point in two-dimensional representation where all the three phases are contacting, that is referred to as nothing but contact point. Okay, and if you take the three-dimensional representation of this phenomenon, so in three dimension we will be having solid surface something like this, and over this we will be having this drop resting something like this. So when this drop is resting, we will be finding that we will be having some circular circumference, and across this circumference we will be having the contact of solid, liquid, as well as the gaseous medium, or three phases. So this particular line which connects all the three phases is called as contact line for a real three-dimensional system. So in two dimension it is appearing as a point, and in three dimension it will be a line over here. Okay, so the motion of this contact line is actually very, very important. And when its occurrence will come, for example, if you are having a solid surface and you are now allowing a drop to touch this surface, so we will be initially finding that shape of the drop will be kind of spherical. If we take ideal configuration, then it will be perfect sphere, and we will be having a point contact. But because of some of the forces, this drop will try to spread over this surface, and it will try to acquire finally some shape something like this. So it means this contact line, which was initially a point, then it has become this circle, then later on it has become some bigger circle. So it means our contact line is spreading on the surface from a point contact to a circle or a circular contact, and it will keep on increasing unless or until the droplet is reaching to the final equilibrium shape. Okay, so its contact line will be moving in radial outward direction. So this is the motion of the contact line. Okay, now the accurate modeling of this contact line motion is actually very, very important for determining the different parameters associated with the heat transfer applications. Okay, now how to model this contact line? So we try to model the contact line with the help of a parameter which is called as contact angle. Okay, so now let us first try to understand the definition of the parameter contact angle. So if say this is a drop, and let us consider this drop is in its final resting position. Okay, means it is not moving, it has reached the final equilibrium state. So when this drop has reached the final equilibrium state, if we measure the angle from the liquid side, which is made by tangent of this air water interface. So this is a drop, say this drop is of water and surrounding is air. So the boundary between air and water is called as nothing but air water interface. Okay, now if I take the tangent through this air water interface at contact point, so this is my tangent at contact point. So the angle subtended by this tangent when measured from the direction of the liquid contact side. So we have to always ensure that when we are measuring this angle we are measuring from the direction of the liquid contact side. So this particular angle is called as nothing but our contact angle. And when this contact angle is measured corresponding to the equilibrium position of the drop, or I should say the resting position of the drop, then this is called as theta E, where subscript E referred to as nothing but equilibrium. Okay. Now this contact angle, depending upon the characteristics of the surface, this solid surface, whatever liquid we have, and its surrounding. So depending upon the properties of these three parameters, the resting position of liquid may be different on different types of solid surfaces. So whenever we do have the combination of these three phases in such a way that our equilibrium contact angle is less than 90 degree, then our surface is called as hydrophilic surface. When our contact angle is greater than 90 degrees, then it is called as hydrophobic surface. So you can see the term philic and phobic. Philic means it wants to attract the liquid. So as it wants to attract the liquid, we will be having more amount of contact point between the, or contact area between the solid and the liquid. Whenever it is phobic, for same amount of volume, you can see in all these three different situations we have same amount of volume, but you can see the contact area between the solid and liquid is actually less over here for theta E greater than 90 degree. And when our contact angle is very high, when it is greater than 150 degrees, in that case we call the surface to be nothing but super hydrophobic surface. And each type of this surface have their different characteristics which helps in enhancement of heat transfer for different types of situations. For example, hydrophilic and hydrophobic surfaces are having a good amount of requirement in case of our boiling heat transfer to increase the rate of heat transfer, whereas super hydrophobic surfaces are very, very important for designing the our condenser units, because on condenser what we want to do, we want to operate in the dropwise condensation mode, and super hydrophobic surfaces are actually favorable for having dropwise condensation, and this avoids or delays the transition to the film condensation regime. Okay, so how these are to be done, that I'll be explaining you subsequently. Till this point, is there any confusion, anything you want to discuss? Okay, so when we have this equilibrium shape of the droplet, this equilibrium shape of the droplet is something which is explained by a very famous equation which is called as Young's equation. Okay, and this Young's equation is nothing but estimated using the balance of the interfacial forces or the capillary forces which are present in the drop. So here you can see this is once again the representation over here. So here you can see this is our one interface, and this is the interface between solid and the liquid. So at the interface between the solid and the liquid, we will be having some surface tension or some interfacial tension which is called as gamma LS, interfacial tension between liquid and solid. Similarly, here we have interface in between air and solid. So here I will be having some interfacial tension force between this solid and gaseous medium. And then this is the another interface we have in between the solid and the gas, sorry, in between the liquid and the gas. So we have some interfacial tension gamma Lg over here. Now, when we talk about the equilibrium, means our contact line is not moving, and for the motion of the contact line, because contact line can move only in horizontal direction, so for the motion of the contact line, because the solid boundary is impermeable. Okay, so liquid cannot enter in this direction. It can only spread in radial outward or radial inward direction. So because of that, for the balance or corresponding to the equilibrium position, all the forces which are acting at contact point or contact line in horizontal direction, that has to be balanced. Okay, so that is what is written over here. You can see this gamma Sg is the net force in left direction, and gamma Ls plus component of gamma Lg means cos theta E component of gamma Lg. This is something which is acting in the right direction. So sum of left forces equal to sum of right forces is something which will be happening at the equilibrium position, and the equation which characterizes the value of equilibrium contact angle using this formulation, that equation is called as famous Young's equation. Okay, however, some of the limitations of this Young's equation are that this is applicable for only the equilibrium position. So when a drop is moving, for example, initially it is like this, and then say after some time it will be like this, after some time it will be like this. So here contact line is moving. So when contact line is moving, it is not applicable corresponding to that situation. Okay, so this is applicable only when the contact line is in equilibrium. This is first thing. And second thing is, this equation works well only if our surface is perfectly smooth. Okay, so this surface has to be perfectly smooth. So it means we don't have any roughness over the surface, and it is a completely smooth and clean surface. But this is something which will not be happening in the practical scenarios. In practical scenarios, we will be finding that we will be having a lot of surface perturbations. At the same point of time, we will be having some dust particles or other irregularities on the surfaces. Okay, so is it clear till this point? Now let me briefly give you idea about the general applications of wetting and spreading on different surfaces. So wetting and spreading means when this contact line is, when this droplet is actually spreading on the solid surface, so up to what extent it is actually wetting this surface. So what are the applications? So applications are painting and coating. So whenever we do put a spray on a surface, so we have to see that, okay, if a droplet of the paint is impacting the surface, so how much it should spread. Okay, then inkjet printing. So in case of inkjet printing also, a drop of ink impacts our paper surface, and on the paper it spreads depending upon the requirement of our actually letter which we want to print. Then water repellent. So for example, when we drive our cars and if it's raining, so what we want, we have to forcefully use the external wiper mechanism in order to remove the droplet from the glass. Okay, so in case of like if we have some surface characteristics of the glass that it is repelling the water droplets, if it is super hydrophobic, allowing the water droplets to leave the surface by its own, so that will be kind of a good application, and it will be saving significant amount of energy also. Similarly, anti-icing and anti-fouling. So anti-icing and anti-fouling are very, very important for our aircraft. Anti-fouling is very important for, say, fouling in different heat exchanger devices, condensers, evaporators, etc. And anti-icing is very important for the aircraft application. So we generally see that if, say, we have some droplets on the wings of the aircraft. So when an aircraft is going to certain regions where temperature is very low, so these will cause the formation of ice cubes on the wings of the aircraft, and this may be detrimental sometimes from the control point of view. Okay, as well as from the power requirement side. So that's why anti-icing is also one of the popular application where we have to design the surfaces in such a way so that droplets should not adhere to the surface. So it means we have to go for the super hydrophobic characteristics so that we should have least contact between the liquid and the surface. Okay. Now let us try to understand in more details about the different applications which may require different types of surface behaviors. Okay, so this first application over here I am showing nothing but from a boiling heat transfer. Okay, so when we have a surface and if we are subjecting heat flux to this surface and outside liquid, if this liquid is corresponding to the T saturation conditions, saturation temperature conditions, we will be finding that there will be initially some bubbling. Okay, so these vapor bubbles will be forming and these will grow on the surface, and when the size of the vapor bubble will be becoming larger, or in order to allow the buoyancy forces to dominate over the surface tension forces, this bubble will leave the surface and rise in upward direction. However, if we increase the heat flux, then bubbling will be more frequent and these bubbles will be coalescing with each other to form the column-like structures. Okay, and if we increase the more amount of heat flux, the bubbles generating from multiple nucleation sites will coalesce in horizontal direction and these will try to form a blanket of vapor. Okay, so this blanket of vapor is actually not good for the amount of consideration of rate of heat transfer, because vapor has low thermal conductivity, so it decreases the rate of heat transfer from the heater surface to the liquid. Okay, so that's why we want to stay more in nothing but our bubbling regime, so that we are having the formation of individual bubbles, and when a bubble is leaving, it is actually replenishing the surface with a fresh liquid. Okay, so that will be improving the rate of heat transfer. Now different types of surfaces are having important considerations in boiling heat transfer. So most popularly in our undergraduate course of heat transfer, we study a famous curve which is given by Mikiyama and is called as boiling curve, which is in between the wall heat flux and delta T. Okay, where delta T is nothing but T surface minus T saturation. Okay, so this curve is having characteristics something like this for constant temperature applications and something like this for constant heat flux applications. Okay, so in this curve we have one important point. This particular point is called as nothing but critical heat flux. Okay, so this is the point up to which we will be finding that we are having this bubbly like phenomenon, and if we increase our superheat or heat flux beyond this boundary, then we will be finding we will be having transition into the film boiling regime. Okay, which we don't want to do, because here rate of heat transfer decreases. Okay, so in order to have high heat transfer, we want to operate on the left side of this curve. So in order to operate on the left side of this curve, we have some requirement of the surface which can actually delay the delay our occurrence towards reaching this critical heat flux. Okay, so let me take up the example of two surfaces. First, if I take say a hydrophilic surface and another side if I take a hydrophobic surface. Okay, so how bubble departure takes place from a hydrophilic surface and hydrophobic surface. So we will be finding hydrophilic means this surface wants more water to stay with it. So if it wants more water to stay with it, the bubble profile in this surface will be becoming something like this. Okay, when it is about to depart. And this is a hydrophobic surface. Hydrophobic surface doesn't want to have more contact of water with the surface. So in this case, we will be finding that for the same amount of volume, bubble profile will be something like this. Okay, so now if you see, the disadvantage of hydrophilic surface is that when bubble will be departing the surface, it will not keep any vapor residue. Will not keep vapor residue. So it means when the bubble will be departing the surface, we will not be having any vapor. We will be having entirely fresh liquid. And when this bubble will be departing from the hydrophobic surface, here we will be finding that we will be having, like, this bubble will leave and it will keep significant vapor residue. So here we will be having some vapor residue on the surface. Okay, so the benefit of vapor residue is that it helps in faster growth of the next bubble. So when we have some vapor already present, it helps in nucleation of the more amount of vapor from this interface and helps in faster growth of bubble. So if we have faster growth of the bubble, our bubble departure frequency will increase and it will improve. It means our vapor will transfer from liquid to vapor state at faster pace. So we will be having more heat transfer rate. So here we will be having more heat transfer rate. So it means boiling over over hydrophobic surface promotes the more rate of heat transfer. Whereas what will be happening, because here we have more amount of spread of vapor. So if, say, from another nucleation site, another vapor bubble is growing, so here these bubbles will be having more tendency to join with each other and form a film. Okay, so the characteristic of hydrophobic surface is that it increases the rate of heat transfer because it keeps some vapor residue, which helps in faster generation of the vapor. But the disadvantage is that because spread of vapor volume is more, so these vapors have more tendency to join with each other and form a film. So it means in case of hydrophobic surface, the occurrence of this type of critical heat flux point will be faster. Okay, whereas in case of hydrophilic surface, though bubble departure frequency is low, but bubble is forming in such a fashion so that the contact between the bubbles will be less. So that's why it delays the occurrence of film formation or occurrence of the critical heat flux point. Okay, so here we can see that the different surfaces are having their different advantages and the limitations. Okay, so due to this, what will be happening, if we have to design the ideal surface for the boiling heat transfer, then we have to try the combination of hydrophilic and hydrophobic surfaces, which we call as nothing but our biphilic surface, so that we do have the advantage of hydrophobic surface, which is high rate of heat transfer, and we do have the advantage of hydrophilic surface, that we are reaching to the critical heat flux very late. Okay, so I do have some videos, but due to this linking issue, I think I am not able to play these videos, so I will not play these. Some of the important videos, whenever required, I will play. Okay, so whatever the concept was there in this video, that I have explained with the help of these schematics. So is there any confusion till this point? Anyone is having any concern or question? Okay, so let me move further. So this is a typical representation that why our different types of surface characteristics, how this behaves with boiling heat transfer. Okay, now another important type of cooling mechanism we have is actually called as spray cooling. Okay, so you can see over here there are different schematic representations for spray cooling. So in case of spray cooling, the fine droplets which are coming from an atomizer are sprayed on the surface. Okay, so and over this surface, actually these will be striking and we will be finding, say, one drop is striking like this, another drop is striking like this. Then depending upon the wettability characteristics, means hydrophilic, hydrophobic or super hydrophobic nature of the surface, these drops will be spreading over the surface. And if surface is hydrophilic and drops are impacting near to each other, this will be forming even a bigger droplets. These will be coalescing with each other and forming a bigger droplet to contact the entire heater surface with liquid. So in case of spray cooling applications, what we want that drops should spread over the surface, okay, and these should also coalesce with each other to form a big film of liquid. Why? Because liquid is having high thermal conductivity. So if our purpose is to remove the heat, then it will be having tendency to take more amount of heat from the surface. And if we do have the occurrence of the dry spot, then corresponding to dry spot, we will be finding that our temperature of surface will be increasing, and if it is going beyond the safe limits, then it may be detrimental for the component which we are operating. Okay, so in this case, we want, in case of spray cooling, we want actually that our entire surface is contacted by the liquid. So we want these drops to spread more and coalesce with each other to fill the entire surface with layer of liquid. Okay, so is it okay till this point? Okay, now this is another important application which is related to condensation heat transfer. So we do know about drop-wise condensation and film-wise condensation. So this is a typical representation of drop-wise condensation. Over here you can see over the surface small drops are forming. Okay, and every time we are seeing that if this is the surface and this is our vapor which we want to condense, then this vapor is directly contacting the surface and it is forming a drop. And if this drop is being replaced from the surface, we will be finding once again the direct contact of the vapor with surface. But if this surface is, say, filled with film of water, and now vapor will not be able to directly contact the surface, but we will be having some thin film over here, and because of this the resistance of the film will be actually coming into picture. Okay, so that's why the drop wise condensation, where direct contact of the substance from which we want to transfer the heat is with the surface, that phenomena is called as drop wise condensation. And where we have some intermediate film and vapor has to penetrate, or heat has to penetrate through this thin film of liquid to reach the surface, that is called as actually film wise condensation. So our aim always in case of condensation heat transfer, or while we are designing the surfaces for condensation heat transfer, our aim is to operate in the drop wise design, so that we can have more contact between vapor and the surface and we can have high rate of heat transfer. So this is the typical representation. You can see over here, this is a cold substrate and here we have water vapor. So these are water molecules and directly contacting the surface. So whenever these will be contacting the surface, we will be finding the nucleation of micro droplets. So small drops will be forming, and further these drops will grow with time, and when these become large, these will try to coalesce with each other. Okay, and once their size has become sufficiently large, these will try to move downward. If say plate is in vertical orientation and gravity is acting in this direction, then because of the gravity these will try to fall in downward direction. So when these droplets will be falling in the downward direction, they may form a film, and once this film is actually forming with the surface, our direct contact of vapor with solid will be decreasing, and in that case rate of heat transfer will also be decreased. Okay, so our idea over here in case of condensation heat transfer is to have super hydrophobic surfaces. So if we have super hydrophobic surface, so what it will do, it will allow the less contact of the liquid with surface, and at the same point of time, once the drop is growing inside, it will immediately try to remove the surface from remove the liquid droplet from the surface. So if we have fast replacement of liquid drop, we will be finding that film will not be forming, and every time we will be having fresh contact of vapor with the surface. Okay, so let me over here show you one video for this condensation phenomenon. Can you see this video?
Yes, sir.
Okay. So here you can see drop is on the left hand side, drop is suddenly leaving the surface, and then once again more number of micro drops are forming. Okay, so this type of phenomenon is actually dropwise condensation. And on the right hand side, you can see that we have a continuous film of liquid, and because of which the formation of micro drops is not there. Rather, the conversion of vapor to liquid is taking place in between the liquid and vapor surface boundary. Okay, so this dropwise condensation is having heat transfer coefficient value almost 10 to 15 times higher in comparison to film wise condensation. Okay, so this is another important application which shows the importance of drop and contact line motions in heat transfer applications. Okay. Now, after having the detailed discussion on relevance of the drop spreading and formation dynamics on different types of surfaces, let us try to have the understanding of some of the practical aspects and how we can actually model these droplets using the computational techniques. Okay, so this is the representation of contact angle on some real surface. Okay, as I told you that we will not be having always the perfectly smooth surface. So we will be having some surface irregularities over here. So like this, you can see over here, we have some irregular surface. Okay, so when the liquid will be resting on the irregular surface, these surface perturbations will be of very small size, say micrometer size. On the micrometer scale, we will not be able to see these small perturbations. So this dashed line, whatever I have drawn over here, this will be nothing but appearing like a nominal surface. So if this is our nominal surface, we will be finding actually the value of contact angle as something like this. Okay. However, in actual practice, if we see our surface is something like this, so actual value of contact angle is actually like this. Okay. So this is the actual contact angle, and this is the apparent contact angle, which is appearing to us considering the nominal solid surface. So we can say that on a real surface, actually our actual contact angle will be different from the contact angle which is appearing to us. So that's why the contact angle which is appearing to us is actually we are calling it as nothing but apparent contact angle. Now, Wenzel was a famous, okay. So this is the difference between apparent and the actual contact angle. Now what happens if we have a perfectly smooth surface? If we have a perfectly smooth surface, for that, if I plot the Gibbs free energy, if I plot the Gibbs free energy of the droplet versus contact angle, we will be finding that we will be having only one minima of free energy. Okay, so we will be having only a single minima on the free energy plot, and this minima on the free energy plot nothing but represents the location corresponding to equilibrium state of droplet. So any droplet that will be showing some contact line motion unless or until it has reached to the minimum free energy state. Once it has reached the minimum free energy state, that location will be nothing but corresponding to its equilibrium state. Okay. Now, for the perfect smooth surface, we have this curve of Gibbs free energy, something like this, and we only have a single minima on this curve. Whereas, if we see the Gibbs free energy curve on a real surface, we will be finding that due to the surface perturbations or surface irregularities, we will be having a number of minima points. Okay, and the we will be having one global minima. So this global minimum will be corresponding to the most stable shape of the droplet. So corresponding to this, we will be having most stable shape, and we will be having some states of the minima where contact angle will be different than the most stable contact angle. Okay, and we will be having the opportunity for the droplet to move from one minima to another minima. So how, if say droplet has to move from one minima to another minima, it has to cross some barrier of energy. Okay, so this much Gibbs free energy is required to move from this state to this state. So this is called as energy barrier. And when a droplet is placed over a solid surface, because of the some instabilities in experiments, we will be finding that we will be having some oscillations with the droplet, and it will be having the tendency to move from one energy state to another energy state. Okay, unless or until it is reaching to the global minimum state. Sometimes we will be finding that, say, drop is resting for some time on a surface, and after that, say, due to wind or any other effect, there is some small perturbation in the surrounding liquid. So because of that surrounding perturbation also, drop may change its state from one equilibrium state to another equilibrium state, or one minimum energy state to another minimum energy state by crossing this energy barrier. Okay, so that's why all these local minimas are called as nothing but the metastable equilibrium positions, and the global minima state is actually the most stable state of the droplet. Okay, till this point it is clear. Now let us try to see that what is the most stable apparent contact angle on rough surface. So the most stable apparent contact on rough surface is given by Wengel. So according to Wengel, when we will be finding this theta y, so theta y is nothing but contact angle measured from the Young's equation. So this Young's equation contact angle will be actually our actual contact angle. However, due to the surface perturbations, we will be finding that we will be having some apparent contact angle which is other than the actual contact angle. So if we have to find out the value of that actual contact angle based on this Young's equation, so we are having this equation which is given by Wengel, and in this equation what we are doing, whatever the contact angle is obtained from the Young's equation, that is multiplied with some factor r to find out the value of Wengel contact angle, and this Wengel contact angle is actually most stable apparent contact angle on the rough surface. Okay, so let us consider that we have this rough surface, something like this, and we have some nominal surface represented by this dashed line, and the drop is resting on this. Okay, so now if you see, this nominal contact area will be nothing but, if say this is the radius r, so nominal contact area A nominal will be nothing but equal to pi r square for this droplet. Okay, however, the actual contact area will be larger than the nominal contact area, because here we are considering this to be straight. However, in actual practice, the contact is more because of the irregularities. Okay, so actual contact area of the droplet will be greater in comparison to nominal contact area of the droplet. So the ratio of A nominal divided by A actual is something which is called as, ratio of A actual divided by A nominal is something which is called as R. Okay, roughness ratio. This is the ratio between the actual and the nominal surface area of the solid. And when this ratio is multiplied with cos of the Young's contact angle, it gives us the most stable apparent contact angle corresponding to the most stable state on this gives free energy hysteresis plot, and this is called as Wengel contact angle. So you can see when our ratio is equal to 1, then this dashed line represents the angle equal to that of Young's contact angle. However, when this ratio is other than 1, then we will be finding for hydrophilic surfaces having theta less than 90 degree, apparent angle, most stable apparent angle is less in comparison to Young's angle, and it will be appearing larger in comparison to Young's angle for theta greater than 90 degree. Okay, is this point clear? So the idea is, if we have to characterize the contact angle on a rough surface, we have to just multiply it with roughness ratio factor in order to find out the most stable apparent contact angle. Okay, similarly we may have different heterogeneity of the surface. So heterogeneity means we may have surface in such a fashion so that the part of the surface, say if some droplet is resting on this surface, so we may have part of the surface with some different contact angle characteristics and part of the surface with some another contact angle characteristics. Okay, so this type of different behavior comes because of the chemical heterogeneity, or another issues, say because of the dust, say some part of the surface is exposed to dust, some part is clean. So because of that also we may have different contact angles in different portions. Okay, so now if say x1 represents the area fraction on some surface where surface tension is becoming say sigma s1, and this x2 fraction is the area fraction of the surface where surface tension is becoming sigma s2. So x1 is nothing but area 1 divided by total area, x2 is area 2 divided by total area, and if we have only two surfaces, then total area will be becoming a1 plus a2. So from here I can simply say that x2 is nothing but 1 minus x1. Okay, so for such type of chemically heterogeneous surfaces, we have this contact angle equation given by Casey, and this final Casey equilibrium contact angle will become x1 times cos theta y1 plus 1 minus x1 times cos theta y2. Okay, and this approximation becomes valid only when the drop size is larger with respect to the scale of chemical homogeneity. So it means our entire drop should not rest on this. So drop should be large in comparison to the this one type of chemical behavior. Okay. Then is one important concept which is called as contact angle hysteresis, and this contact angle hysteresis actually requires the importance of dynamic contact angle modeling for accurate modeling of the contact line dynamics. Okay, so this is one schematic representation of a drop. You can see this is a drop surface, and here we have some nozzle, and with the help of this nozzle we are injecting more amount of liquid in the drop. So when we will be injecting more amount of liquid in the drop, we will be finding that this contact line is actually sticking to the surface, and when we add the liquid, this liquid is actually getting piled up in upward direction like this. Okay, and we will be finding one situation when this drop will suddenly move in forward direction after a contact angle reaches to some maximum value. Okay, so during the sticking of the contact line, when we add more liquid, the volume of drop increases and the contact angle value also increasing, and a critical value of contact angle beyond which pinning of droplet line is not there, and contact line has started moving in radial outward direction. This maximum value of contact angle is called as nothing but advancing contact angle. Okay, so this is called as advancing contact angle theta A. Similarly, if we now take out the liquid from this drop, once again contact line will be sticking like this, and we will be finding that drop volume will keep on decreasing, something like this, and value of contact angle will also keep on decreasing. But after a minimum value of the contact angle, we will be finding that this contact line will retract in radial inward direction and it will pin to some another new location. Okay, so the minimum value of contact angle at which this happens on a surface, that is called as receding contact angle. And this type of motion of the contact line, where it sticks to some surface, then it either extends or retracts, is actually called as stick slip motion. Okay, and this stick slip motion, in this stick slip motion, the value of the angle at which this forward or backward movement of the contact angle of the contact line will happen. It's a strong function of this motion of the contact line, and that is called as contact line velocity. Okay, so it's a strong function of contact line velocity. So here you can see, say this is our contact line velocity. So this is contact line velocity equal to 0. So for velocity greater than 0, we will be having some advancing contact angle, and for contact line velocity less than 0, our value of contact angle will decrease. And corresponding to 0, we will be 0 velocity, we will be finding that we are having some hysteresis of contact angle. It means if we move in advancing direction, it is advancing at some higher value of angle, and if we do receding, it is receding at some low value of angle. Okay, so this difference of theta A minus theta R is called as nothing but contact angle hysteresis. Okay, so from this discussion, we have come to know one important point, that our angle of the drop motion is nothing but a strong function of this contact line velocity. So it means if in a drop, while contact line is moving, if the velocity of the contact line is changing, so value of this contact angle will also keep on changing. So that's why this contact angle is being called as nothing but dynamic contact angle, and this dynamic contact angle is different than the static contact angle or equilibrium contact angle, which is defined by the Young's equation. So it means when we are having the moving contact lines, we have to actually determine the value of this dynamic contact angle to accurately model the spreading and retracting motion of the droplets. Okay, is this point clear? Is it okay till this point? Okay, if you have any questions or confusions, that you may please ask. Let me check chat box if anything is. Okay, so I hope you are understanding whatever I am trying to convey. So let me once again repeat over here. So the overall idea of this contact line modeling is that the motion of the contact line is having actually strong control on the value of the contact angle, which is actually which we are getting. Okay, and depending upon the velocity of the contact line motion, the value of the contact angle changes instantaneously. So that's why the contact angle over here I am referring to for moving contact lines is dynamic contact angle, and the accurate modeling of the dynamic contact angle is very important if we have to determine the accurate dynamics of the droplet, which may have significant control on the different heat transfer parameters. Okay, so now there are some models developed by different researchers to determine the value of this dynamic contact angle. So let me represent the functional relationship of dynamic contact angle. So dynamic contact angle is a strong function of equilibrium contact angle of the surface, advancing contact angle, receding contact angle for a surface, and viscosity of the drop liquid. And another important parameter we have over here is actually capillary number. Okay, so capillary number is a non-dimensional parameter which is obtained by the balance of surface tension and the viscous forces. So its value is mu UCL divided by sigma. Here sigma is interfacial tension, okay, and mu is coefficient of viscosity, and UCL is contact line velocity. Okay, so contact line velocity is actually, if I say my drop is initially like this, after some time it is like this, after some time it is like this, so it means this contact line is actually moving in radial outward direction. Okay, so the velocity with which contact line is moving, that is called as UCL, contact line velocity, and it has significant control on the modeling of the dynamic contact angle. Okay, so for the drops, if we have say some liquid droplet and it is spreading in the surroundings of air. Okay, so if a drop is spreading in surrounding of air, for modeling its dynamic contact angle, there are different contact angles available, models available. So one of the very famous models is Kistler's dynamic contact angle model, according to which dynamic contact angle is nothing but Hoffman function of x, where x is capillary number plus reverse Hoffman function of theta m, and the definition of Hoffman function is given over here. Okay, and here this type of equation is applicable for both the advancing and receding case. It means irrespective of the fact if the drop is moving in radial outward direction or in radial inward direction, this model will be actually applicable. Another famous model is Cox model. So as per Cox model, the function of dynamic contact angle is equal to function of macroscopic contact angle plus capillary number into ln of L by lambda, where L is actually our macroscopic length scale and lambda is microscopic length scale. Okay, so the difference between the macroscopic length scale and microscopic is when a drop is resting on a surface, it will be having shape something like this. So the reason very close to the solid surface, we call in this region length scale to be lambda, microscopic length scale, and if we consider the length scale of the order of size of the drop, that we call as nothing but macroscopic length scale L. And for drops which are spreading in air, as per the Cox's model, g of theta can be approximated as theta cubed by 9. And this is also applicable for both advancing and receding contact lines. Then another model is there, Sikh-Morozev's model. So Sikh-Morozev's model is applicable only for the advancing contact lines. Okay, so these are the different models which are initially started with some of the hydrodynamic theories by dividing the droplet into multiple parts, and then later on their functional relationships are derived by taking some of the experimental support and empirically deriving these functional forms. Okay, so these models, whatever I have shown over here, these are only applicable when we have a liquid drop in presence of air. And another situation we may have that we have some one liquid, one as drop liquid, and surroundings also we may have some another liquid as say liquid 2. So for this type of situations, we will be finding that viscosity of drop divided by viscosity of surrounding. Or I can take it other way. If I write viscosity of surrounding divided by viscosity of drop. So for air water system, viscosity of surrounding is nearly equal to 0. So this viscosity ratio is actually nearly equal to 0. However, if we have some another surrounding liquid, then viscosity of that liquid cannot be neglected, and there we will be having the ratio of these two viscosities as some finite value, and we cannot employ the same models for that type of situation. Okay, so how to model that I will show you in the later parts. So it means one thing is very, very clear, that if we have the motion of the contact line, we require knowledge of dynamic contact angle. Value of dynamic contact angle is strong function of contact line velocity, and to determine, we do have different models available in literature. Okay, now we have to implement these models into our numerical formulation to find out the motions of the moving contact lines. So this is actually a theoretical background how these contact angle models are determined. So I will not go into much details of this, and you may refer to some of the literature related to this detailed discussion. Okay, now let me talk about numerical modeling of the moving contact lines, and for numerical modeling, how we are, what equations we are solving and how we are solving it. Okay, so like in case of solid mechanics, we have some governing equations to solve the our dynamics of the system. Similarly, for fluid systems also, we require some governing equations in order to determine the dynamics. Okay, let me now take a simple example. Say I have a spherical drop of of liquid or water. Say I have a water drop, and in surrounding I have air, and here I have some solid surface. So obviously what will be happening when this spherical drop will be touching the solid surface, it will be spreading on this surface, and its final or equilibrium angle will be having some value which is characterized by the Young's equation. Okay. Now, let us consider that we want to do a numerical simulation where we want to study the spreading dynamics of this droplet. Means we want to say at this point, its contact radius is 0. Here we have some contact radius RE, and in between we will be having some contact radius say R as function of time. So this is corresponding to t equal to 0. Say this is at some time t equal to t1, and this is at some time t equal to t equilibrium. Okay, so what will be happening if we just plot this r as function of time? We will be finding it will start from 0, and then it will be finally reaching to some equilibrium position. Okay, say radius corresponding to this is RE. So it will be reaching to some equilibrium position. Now, if we have to understand the dynamics of this, we are interested in knowing that how this droplet is actually reaching from this point to this point. How means it may reach like this. It may take this path. So say this is path 1, this is path 2. It may take some another path 3. It may take some path like this, path 4. It may take some path like this, path 5. So what is the path of this droplet to spread? Actually, we are interested in that, because if it is taking this path, it means for majority of its spreading time, only the contact is very less, and then suddenly the contact has increased. If it is taking this path, it means immediately it has spread it, and then finally it has actually gone to this equilibrium shape. Okay, so this, if I am trying to do it for say spray cooling applications, then this path number 4 is not good, because for the same amount of time here we have less liquid contact. However, through path number 5, for the same amount of time we will be having more amount of liquid contact. Okay, so that is something which we want to tune also, and we want to also know that what path it is taking. Okay, so to find out its accurate detailed dynamics, because it has direct impact on the heat transfer applications, we want to perform some numerical simulations. Okay, so if I want to perform the numerical simulations, obviously what I have to do, I have to find out first what are the governing equations. Okay, so in case of liquids or gaseous mediums, in general, if I call in case of fluids, we have to solve two important equations. One is continuity equation and another is momentum equation. Okay, so for incompressible flow situation, this is our continuity equation and this is our momentum equation. Now we will be finding that in this system we have actually two fluids. If solid, I am just modeling as a boundary. So I have two fluids, air and water. So in between these two fluids, we will be having some interface also. And at the interface, we will be having interfacial tension force. So this FSI over here represents the interfacial tension. If we are performing this experiment in presence of gravity, then body force over here is nothing but gravity. This is the viscous force, pressure force, and this is our inertial force or advection force because of the acceleration of the drop liquid. Okay, so this is our momentum equation. Now what we have to do, if you see over here, we are writing one continuity and one momentum equation, and in this we are using some fluid properties rho and mu. However, we have two fluids over here. So how to solve this? So for this we are using this volume of fluid method. So what we do in case of volume of fluid method, say this is my drop and this is my air, and say this is my grid over here like this. Okay, so what I will be doing in this grid, I will be defining one parameter alpha, which is nothing but volume of drop divided by volume of the cell. So here you can see this cell is completely filled with drop. So here ratio of volume of drop to volume of cell will be 1 for all the liquids, for all the cells which are completely filled with drop. Where we don't have any drop liquid, here value of alpha will be equal to 0. Okay, so in all these cells, value of alpha is 0. And then the cells where we have combination of drop and liquid, they are depending upon the volume of liquid, we will be having fractional value. Okay, for example, here say we have about 0.4 as value of alpha. Fine. So what we will be doing now, if I know the distribution of this alpha, then based on the distribution of alpha, I can determine some volume averaged property in each computational cell. Okay, and that volume averaged property is given over here like rho equal to alpha into rho 1 plus 1 minus alpha into rho 2. So wherever we are having value of alpha equal to 1, there it will be taking density of drop, and where we are having alpha equal to 0, there it will be taking density of air, and where we have the combination of the two, then depending upon the volumetric averaging of the quantities, we will be getting some intermediate value of density and viscosity. So this is a way to tackle the two-phase situation with the help of a single continuity and single momentum equation, which is actually defining some volumetric averaged properties. And also we will be finding, say this is corresponding drop shape corresponding to some condition or some time t1. Now at another time t2, what will be happening? The drop shape will be changing. Okay, so it means the value of alpha should also change. So in order to determine the value of alpha, we have one additional equation which is called as advection equation of volume fraction. So this is advection equation of volume fraction. So this volume fraction equation, what it will do, it will try to tell us that how this alpha is changing with time depending upon the value of velocity at the interface. Okay, so this will be governing how alpha is changing, and it will, if we know the distribution of alpha at different times, we will be able to determine the value of the properties at different times. Okay, till this point it is clear. If you have any question, please let me know. Okay, so till this point, we have seen that what are the governing equations which we have to solve. Now, we have to initialize. So while the drop will be moving, its contact line will be moving something like this. So when the contact line is moving, we have to specify some value of contact angle as boundary condition. Okay, so we have to assign some boundary condition which will be telling us that when this interface is touching the drop, for example, interface may be like this, at same time drop may be like this, at same time drop may be like this. So depending upon the value of the dynamic contact angle, actually we have to supply a boundary condition at this solid surface which will be determining the shape of this contact angle. Okay, so for that, what we have to do, we have to supply the boundary condition with the help of dynamic contact angle models. So in the present lecture, whatever the cases I will be showing, for these cases we have actually used Kessler's dynamic contact angle equation. So this Kessler's dynamic contact angle equation is implemented on the bottom wall, and we have considered when contact line velocity is greater than 0, then in Kessler's equation theta m must be equal to advancing contact angle, and when UCL is less than 0, then theta m equal to theta r. Okay, and theta a and theta r for different drop and solid surface combination we have actually experimentally determined, and these are supplied as a boundary condition. Okay, and what is our simulation domain? So because spreading of droplet is a symmetric phenomenon, if we take the ideal condition, so it's a axisymmetric situation. So we have taken the axisymmetric simulation domain. At this point we have supplied symmetry boundary conditions, and this is our drop liquid initially initialized, and 2r is the initial diameter of the droplet, and at this wall we have specified no slip boundary condition, and for contact angle we have specified the Kessler's equation, and this is our large domain. So we have taken this domain sufficiently large in comparison to the radius of the drop, so that walls should not influence the spreading dynamics of the droplet. Okay, so now we will see over here that how this drop is actually spreading and finally reaching to the equilibrium condition. So it means, as I told you earlier, that this r versus t may take different path. So which of the path this r versus t is taking, that is what we are trying to determine over here. So here let me show you the simulation video. So this is the spreading detailed simulation video. So let me show you. So you can see this is how drop is spreading. Can you see my video?
Yes, sir.
Okay. So this is how the drop is spreading over the surface. So you can see initially, and then finally what is the shape. And now if we do plot its r versus t, that will be telling us that which path this droplet has taken. So this plot over here shows the path of the droplet. Okay, so these red colored, these blue colored dotted points are nothing but experiments done by Mitra and co-workers in 2016, and this red colored point and line represents actually simulations done by us, and this work is recently published in journal Language, and this work is done by my MS student Mr. Devashri Devnath. So here you can see that in this R versus T, in the initial portion of the droplet, the relationship between the R and T is of this scale. R is of the order of T power 0.84. Then later on we are having this relationship in between R and T is of the order of 0.51, and finally then it is reaching almost to equilibrium, and R is of the order of T power about 0.1. Okay, so these are the three different stages of spreading dynamics of the droplet. So you can see initially it is spreading at faster pace, then its pace is decreasing, and finally near equilibrium its pace is very slow. Okay, so now depending upon the balance of the forces across the contact line of the droplet, we will be finding that initially it is balanced but between the capillary pressure and the viscous force. So because of which we will be finding that R will be almost of the order of T to power 1, which is coming as close to 0.84 in our simulations. And then after some time, if we balance inertia force of the drop with the capillary pressure, then we will be finding that, so here this has to be gamma actually. So here then we will be finding that it will be actually giving us R of the order of T1 by 2, which is coming as R of the order of T.51 in our simulations. So this initial regime of drop spreading is called as initial viscous regime. Then second regime is called as inertial regime, because here inertia force is balanced by the capillary forces. Okay, and finally when R is of the order of T.1, this type of regime is famously known as Tanner's regime of drop spreading. So this near equilibrium Tanner's regime of spreading is known long back. However, there was the confusion in between the initial two regimes, whether some of the people said, because they were not able to resolve the dynamics in this low time zone experimentally, so some of the people commented that okay, drops reaches the Tanner's regime immediately after the inertial regime, and it initially starts in inertial range, but the recent experiments and our simulations shows that initially the spreading starts with viscous regime, then it transforms to inertial regime, and then it transforms to near equilibrium Tanner's regime. Okay, so this is the typical spreading dynamics of droplet under adiabatic flow conditions, under adiabatic situations in presence of air. Then we have seen the effect of different parameters. For example, this is the effect of initial radius of the droplet. Then we have used two different time scales, viscous and inertial time scales, to non-dimensionalize, and we found that initially the dynamics is for all the size of the droplets, initial dynamics is viscous dominant, and then later dynamics is actually inertia dominant. This is the effect of viscosity, how viscosity changes the motion of the contact line. So you can see that for high viscous drops, the instantaneous contact angle moves very gradually, whereas for low viscous drops, we are having significant oscillations in the instantaneous value of the contact angle. So what is instantaneous contact angle? Basically, initially when drop will be spreading, its contact angle will be close to 180 degree. Then with time, as it will keep on spreading, its contact angle will keep on decreasing. So that dynamic contact angle is plotted as function of time. Okay, and why its value is decreasing? Because dynamic contact angle is a function of contact line velocity, and contact line velocity is actually changing. Okay, is it clear? So this is the effect of contact angle. So if we change the contact angle, how it affects the dynamics. So upon changing the contact angle for same volume of droplets, you can see on a hydrophobic surface, the spreading is kind of uniform, and on a hydrophilic surface, we are having the formation of this upper neck-like structure, and here we will be having the formation of some satellite droplets, which will be leaving the leaving the complete volume of the drop liquid. So this is the effect of surface tension. I will not go into much details. Rather, I will try to explain you one more physical scenario. So this is how the secondary drop is pinching off. So its motion is actually controlled by the balance of Rayleigh-Taylor instability. Okay, now another important situation is under liquid drop spreading. So the meaning of under liquid drop spreading is, as I told you earlier, that we have drop of some liquid 1, and then in the surroundings we have some liquid 2. Now whatever earlier contact angle models were there, for all these models we were having a situation where viscosity ratio of surrounding to the drop liquid was negligible. But for this situation, the viscosity ratio is not negligible. So due to this, our earlier models will not be applicable. Okay, so in this study, actually, we have first tried to develop the contact angle model for these different liquid-liquid combinations, and then we have implemented in our numerical model to solve the under liquid drop spreading dynamics. So Cox has given this famous equation f of theta lambda equal to f of theta m lambda plus capillary number, capillary number into log of L by Ls. Here, this lambda is nothing but the viscosity ratio. Okay, so what we have done in our cases for different, and if you see the functional form of f, so functional form of f is, so here this epsilon is nothing but lambda only. So this is a typo. So here you can see that this f of theta comma lambda is integration 0 to theta 1 by g phi epsilon phi lambda into d phi. And this is the function g phi comma lambda. So in this function, this particular function we have actually tried to fit using some power law model, and this we have fitted for different values of lambda depending upon the combination of the drop and the surrounding liquid. For example, the two of the combinations are listed over here, where we have a DBP oil and dodecaine oil drops which are in the surroundings of water, and viscosity ratio for the first case is 1 by 16 and for second case is 1. So after fitting this power law model for this function, we have actually integrated this equation and finally obtained the contact line equations for under liquid scenarios. Now these contact line equations are given as boundary conditions in our simulations. So the only difference was taken in our simulation is that drop is of DBP oil and surrounding in place of air is now water, and this equation is substituted for the boundary condition on the bottom surface. Okay, so once we substitute this by considering this type of simulation domain, you can see over here the details are given. So we will be finding the drop spreading dynamics for different types of drops. So you can see that we are finding that drop is actually initially starting with inertial with the near viscous regime, then we have some inertial regime, close to inertial regime, and then we are finally having tenuous regime. But this inertial regime is only applicable for this dodecaine drop, for which viscosity ratio with surrounding liquid is equal to 1. However, for other smaller viscosity ratios, we are mainly having the presence of viscous regime, and after viscous, transition is taking place into the tenuous regime. We are not having occurrence of this intermediate inertial regime for the another small viscosity ratios. Okay. And this is typically shown that if we use some effective viscosity based viscous scaling, so for all these three small viscosity ratios, we are having some self-similar behavior, which says that the entire spreading dynamics is actually staying only in the viscous regime before transitioning into the tenuous regime, and it is not actually entering into the inertial regime. So this is the difference of spreading dynamics in between air and water. So for air, you can see that we do have a profile something like this, whereas for water, actually spreading dynamics is a bit slow, and at the same point of time, spreading in the surroundings of water is not having presence of intermediate inertial regime. Okay. Is it okay till this point? Any question? I do have one more case of drop impact over super hydrophobic surfaces. So here you can see this is a super hydrophobic surface, and when drop is impacting, its contact angle will be very high. And we are studying the impact dynamics on these super hydrophobic surfaces. These are the simulation domain and boundary conditions. And let me show you some videos. So for example, this is the experimental video of drop impact on a super hydrophobic surface. So here you can see this is a droplet. Can you see my video?
Yes, sir.
Okay, so here you can see this is a droplet, and this drop is impacting on a nanotube surface, and you can see this is how the drop is impacting, and then it is bouncing from the surface and leaving the surface. Okay, so one of the very good applicability of this is for our actually designing the windshields, or I can say that designing the glasses of our automobile. So if our automobile glass surface is hydrophobic, we don't need any wiper. When the drop will be impacting, if it leaves the surface, we will be finding that we will not be having droplets staying on the glass. Okay, and we need not to use any wiper. So self-cleaning of the surface will take place. Then you can see this is our simulation of drop spreading on a horizontal super hydrophobic surface. So you can see that here drop is completely lifting the surface. Okay, and similarly, like experimental video, we have one animation for drop simulation of drop impact over super hydrophobic surface also. So here you can see this is how a drop is sliding over the surface, and then it is actually bouncing the surface. Okay, so here also determination of contact time is very, very important for how long the drop is actually contacting the surface. So so you can see that experiment versus simulation, contact time on a horizontal surface, and this is the validation between experiment and simulation. And this is the comparison between simulation and experiment. So this is our experiment on inclined surface as well as our simulation. So it also shows once again a good match. This is how the bouncing is actually taking place. In some cases, we have symmetric bouncing when drop is actually bouncing with symmetric profile of the jet. In some cases, we have asymmetric bouncing where drop is taking very random type of shape, and in some cases we are having breakup of the drop into two parts while it is actually leaving the surface. So depending upon the behavior of its impact velocity and the angle of inclination, we have divided this based on the simulations. We have found some design map. So in this region we have symmetric bouncing, then when we have high inclinations, then bouncing is asymmetric, and even breakup is taking place when impact velocity is very, very high at almost all the angles of inclinations. This is the relationship for contact time as function of impact velocity, but I think now time is over, so I will not go into much details. I will just browse through these slides, and I would like to acknowledge Mr. Devashri Devnath. Actually, majority of the works are taken from his thesis over here in this presentation. And I would also like to thank you all for listening me patiently.
So, thank you, Dr. Pramod, for this very informative and productive session. So, if there is any question from participants, then they can ask.
Yeah, please, you can ask questions. And if, say, at present you are not having any question, and later on, say, once again, after going through the lecture, you are finding some difficulties, you can write to me also. My email ID is given over here. And details about some of these works you can find in my publications also. So on my web page, the publication details are listed.
So, I think there is no question right now. So, we may close this session, and next session we will have at 2:30 p.m. Thank you, Dr. Pramod, for sparing your valuable time for this workshop. Thank you very much.
It's my pleasure, and thanks for the invitation.
Thank you. Thank you.